Hello and welcome to this manufacturing systems technology module 32. We were talking about numerical control machines, and basically what we discussed in the last class was that they are no different than ordinary machines, except the fact that the relative tool to workpiece movement is now controlled through a controller process, and the human interface is avoided between the controller and the machine, although there is obviously a human interface between the controller and the external system which wants to develop a certain design in a machining center. So this is sort of a most recent picture borrowed from a textbook of an NC machine. Okay, it's called an NC lathe, and you can see the if you do a line diagram or a schematic of this particular machine, it is basically different than a conventional machine only in terms of this whole unit right here, which is actually the controller unit. Okay. So obviously the controller needs to communicate with the external world, so you have some kind of a switchboard for controlling this controller, and you have a control panel on this particular way that you sort of give signals to the controller, and remaining everything else including the lead screw, the cross slide, the saddle, the tail stock, the head stock, whatever, is just as a conventional machine. So this gives you an illustration of how NC machines are quite alike technologically to the conventional machines. So if we look at the various ways in which the automated operations within an NC system happens, there are two different kind of motion control which are generally executed within the whole NC domain. One is given by a DC motor, direct current motor. Another is more like a stepper motor which works on voltage pulses, but you have very good control of these stepper motors in terms of number of pulses that you are providing and their actual rotation or actual movement, and these are all rotational to linear movement converted in terms of different lead screws, etc., all inbuilt as a capability of the NC system. So typically what you otherwise were earlier achieving in a lathe machine with an operator operating onto the cross slide by means of a lead screw by rotating it with some number of rotations so that there is a linear movement, is now achieved by that stepper motor or DC motor. So stepper motor is mostly for the fine positioning, DC motor being a high torque motor is mostly for the regime where you have to have actually the cutting forces, the stresses, etc., executed to the particular machine. So if you look at the way that these motors are controlled by the controller, there are principally two different control systems which would exist. One is an open loop control system, another is a closed loop control system. So obviously open loop control system, I think we are quite aware how this type of control works, is used with a special stepper motor, and open loop meaning thereby that there is no feedback signal. Obviously stepper motor is very accurate, so you can actually know how much it has proceeded linearly by means of how many pulses has been provided in the stepper, because the stepper actually turns exactly so many degrees of rotation after one voltage pulse has been given. So it is a very correctly controlled, very precisely controlled motoring system. Okay, so in this you have signals in form of current pulses, okay, and they are sent from the MCU or the main control unit to the individual motor being controlled, and there are many such stepper motors all round the whole NC system which would allow it to have this relative motion control between tool and workpieces as needed, and each pulse would result in a finite predetermined amount of revolution, very precisely controlled. So you don't have an undershoot or an overshoot problem in this particular case. It is exactly the degree of revolution that you want it to have is achieved at the end of the whole pulsating signal. Okay, and then the pulse is cut off, then automatically there is a quick stoppage. There is hardly any braking effort or any time delay which happens between analogously between the point when the voltage, the current pulse is gone and the motion of the motor is still continuing. So there are hardly any inertial components of load associated with such a stepper motor. It's a part of the design of the stepper motor system. That's how it is designed actually. So you cause a specified amount of movement and the control system determines how many current pulses are required, and sends precisely that number of current pulses to the motor. Okay. So you don't need really an end positioner kind of a position reader kind of a system in this case, because you are already quite sure of the preciseness at which the rotation would convert into some kind of a translation, and you are quite certain that the lead screw would reach a certain position in that particular system. So thus the control does not need to monitor specifically where the motor is located. It is assumed that the required motion is achieved if correct number of pulses is sent, and that is how the distribution of the signal, the current signal, is carried out by the MCU to such stepper motors. Only you need to, the control system only needs to keep track of how many revolutions the motor has gone through by knowing the counts of the number of current pulses, and from that you can actually calculate very accurately the motor's position with respect to time. Okay. So that is how this whole business actually works in case of NC control open loop control systems. On the other hand, for some of the high torque applications, as I was telling in machining, we need servos or DC motors, and which have analog or variable speeds, and they are used in this sort of a closed loop controlled manner, because you exactly now need to ascertain where the positioning has happened at the end of the whole DC cycle. Okay. And therefore you need to know exactly the position of the motor in terms of the rotational angle executed, okay, after the signal has started till it actually stops. So you can, the advantage is that you can have very high level of torques, because that is what an advantage is with the DC motors. Obviously you can reverse the motor, that is another very big advantage in this particular case, that you have a reversal, but they cannot be caused to move in very precise amounts. Just as we were seeing in the open loop case earlier, the precision of stepper motors cannot be executed by DC motors. There is always an undershoot or a overshoot kind of a situation where the motor may just end a few more degrees to what it was required to traverse, okay, because of its own inertia, etc. It takes some time to brake, and this is realistically not a quick start quick stop kind of a system. So in order to keep track of the position of the motor, you need a separate position sensor, which is also known as a resolver, and this has to be fitted definitely to monitor how the motor is performing in terms of its position. And the signal is now fed back. Okay, so that is why it is a closed loop, that this signal in a closed loop manner is fed back, and the motor can be sometimes even reversed in order to accurately come back to the position in question. Okay. So this positional information obviously from the resolver would be compared with the target position, and the errors are then determined accordingly. Because DC motors can be reversed instantly, it is possible to correct any positional error detected. So if there is an overshoot in some particular case, you can obviously send a reverse DC signal by changing the polarity, and let it actually now in a very slow manner go to the accurate position from where it had actually overshotted. So this is about what the controller does to the machine. Okay, so the controller actually is now responsible for sending either short current pulses or DC current for these different kind of motors to be operational, so that there is a lead screw motor arrangement which is now moving relatively the workpiece and the tool. Okay. The other side of the controller which needs to be really worried about is the side where you want to command the controller to do something important and useful, and that is how your controller primarily on the whole machine system remains, which leads you to make what you desire to make through the NC machine. Okay. So therefore in some manner you have to start interacting with the controller and develop a language for the controller to understand logically, and there is where this programming of NC machines comes very handy into picture. And therefore you have to first of all develop a coordinate map based numerical data, and then be able to organize your commands or your communications in a very effective manner, so that the controller understands you and repeats that understanding every time you have said something alike. So therefore a language evolves in that, and it is called the NC programming language, based on which you can actually start controlling the machine control unit or MCU. Okay. So the process of writing an NC part program is also known as NC part programming, and merely it just means the part program just means that you are writing it for an engineering part. you do not think it or do not misread it as part of a program or a partial program or a subroutine, nothing like that. The part program simply means that you are programming the whole NC system, the numerical control system, for developing an engineering part, and that is why the term part programming has been mentioned here. Okay. So the NC part programming is typically done by a person who is responsible for writing this instructional code, which is very conveniently read by the controller, and that person makes a code, and then this code repeats thousands of times and generates as many parts with the same kind of precision and accuracy as is desired by the concerned person. So therefore it is a kind of an automated way of manufacturing. So what all does a part programmer need to know in advance before starting such a programming activity? So the NC part programmer should need to have definitely knowledge of a wide range of manufacturing processes, and it should also be able to possess a skill as a machine operator, so that you may be able to see some of the shortcomings of metal to metal machining processes which would otherwise occur in conventional tools. So she needs to have a thorough knowledge of capabilities of the machine with which the program is to be written. For example, he needs to know about what is the accuracy within which, what is the surface finish, or what is the accuracy within which you need to operate. He also needs to have a data about the feeds and speeds at which optimum material removal would happen, and all these have been, I think, in a way illustrated earlier in our CAP process. So all this information comes from that operator knowledge which has been embedded into a computer aided process planning system given earlier. So this ensures that the program written makes the maximum use of machine's capabilities without violating its technological constraints, and obviously there are going to be the cutting tools, the jigs and fixtures, the available labor, any other material handling equipment such as robots, automated guided vehicles, all these as a part of the manufacturing environment, which somehow need to be again trickle down to the programmer's knowledge base for it to be able to, in a very effective way, manage this whole so called machining operation, the part which the controller has to be communicated and left alone for doing, okay, with respect to the particular machine which is giving the deliverables. Okay. So in writing a part program, the programmer generally starts with obviously an engineering drawing of the part, and this drawing is read in some kind of a orthogonal coordinate system, where this must be interpreted to determine the individual operations that should be performed on the workpiece to produce a final component according to the design specification. Okay. And this is the basis used to determine the order in which the operation should be carried out, establish the cutting conditions to be used in each machining operations, determine the associated non-machining operations such as tool changing, machine setup, coolant use, etc., and select the appropriate jigs and fixtures to be used to hold the workpiece as the machining is being done. Okay. So in a nutshell, these are some of the important steps that a programmer starts with. So arranges the engineering drawing and determines the individual operations, and also sort of establishes conditions of machining, etc. You can borrow it probably from your earlier CAP determined strategies, etc., so that you can start doing the NC programming. So the first thing which is of importance for me to discuss here is how you actually try to give a coordinate frame in which you have laid out the drawing or the design, and how you now try to define the motion sequence in that coordinate frame as a function of positive distances and negative distances along the different axes of motion. Okay. And these are sort of nomenclatures, these are standard conventions which are used world over to produce NC systems, which would generate that how this part would move relatively with respect to the tool, okay, or the working tool in such a NC machine. Okay. So the first movement which is recorded is typically along the Z axis, which is the most important axis for machining, and it is always aligned with the spindle that imparts the cutting power. So for example, in a lathe, the spindle holds a workpiece and rotates a workpiece. In the same instance, if you look at something like a face milling system, the spindle is actually responsible for rotation of the tool. So it really doesn't matter whether it's the tool or the workpiece, but the spindle generally is the unit in any conventional machine which is going to give the cutting power, which is going to ascertain that machine material removal takes place at a certain rate. Okay. So, one thing is very clear here, that the z axis is always the axis of that spindle which gives or delivers the cutting power, and you have to just consider that so if supposing there is a workpiece on the surface of a table, and let us say there is a face milling operation where there is a milling tool coming from the top in this workpiece. So, if you are moving away from the workpiece, okay, so if you are moving away from the workpiece, it is always signifying a positive z direction, okay, and if you are moving into the workpiece, it is always signifying a negative z direction. So, this is how you program the coordinates, so that now with a stepped approach and a given convention, every time you are reading out only the coordinate data which is coming from the drawing or something which has come from the last step of the cap, okay, and based on that readout of the numerical data, you are actually ascertaining whether there is a certain direction of movement relative with respect to the tool to the workpiece. So, in the case of a milling machine, for example, there is a face milling, obviously the cylinder, the spindle is the z axis, that is what we said, and if you see that if positive z motion tends to increase always the separation between the tool and the workpiece, that means the tool is going away from the workpiece, it is going in the positive direction, in the z direction, and if it is going into the workpiece, it is going in the negative z direction. So, given this z axis, now if we can define only one other axis x, obviously in a 3-dimensional orthogonal coordinate system, if the z and x is known, automatically the y can be known. Okay, so, we will go to the next step now, which will say how to do the x axis readout. So, the x axis is again the principal axis of motion in which moving element is positioned. It is parallel to the work holding surface, and it is arranged to be horizontal if possible. Okay. So, on machines with rotating work pieces, for example lathe, etc., it is radial on parallel and parallel to the cross slide, and on machines with rotating tools, for example milling, etc., the positive x is always, now when we are having this such a tool, I had always mentioned that the spindle is in the positive z direction when it is moving away from the workpiece is kept like this. So, now the tool is, if you look at the way that the spindle is mounted, it is always mounted in some kind of a column which is there in the back end of the machine, which is away from the workpiece. So, with that column on board, if you are rotating the spindle, and this is the positive z axis where the work, it is going away from the workpiece in this direction, to your right is the positive x axis. Okay. So, obviously if you have the positive z and the positive x, you would automatically be able to ascertain what is the positive y. So, we will do this in more details in the next module. In the interest of time, we are closing down this module at this point of time. Okay, so, in the next module, we will start again from looking at some of these principal directions and develop a good nomenclature. Thank you.